Christine G, and I'm going to be going over this problem out of Mod 6. It's number 13, and sometimes the numbers don't match up, so it could be that it's better to look for 4.3.23 in Pearson My Stat Lab. So we have this data that represents the weights of various domestic cars and their gas mileages in the city. The linear correlation coefficient between the weight of a car and its miles per gallon in the city is R equals negative 0.992. And then it also gives us the least squares regression line right here, calculated out nicely. And then it asks us to work through parts A through C, and it gives us the data table. So first of all, it asks what proportion of the variability in miles per gallon is explained by the relation between weight of the car and miles per gallon. So for that, we would look for the coefficient of determination, and so we would get that by squaring this number R. And so let's go ahead and get that one, and then we'll talk about that a little bit further. So we've got 992, and it's negative, and then I need to square it, and then I'm coming up with 98.4%. Oh, I put that percent sign in there. Okay, good. Okay, and what this number tells us, it's the 98.4% of the total variation is described by the variation in X, or the weight of the car. So that's what that tells us. And to get more information on that, I recommend looking at your textbook, because that would be quite a bit of information that to learn about and see how it works. There are a number of calculations that are done behind the scenes in StatCrunch in order to calculate that number, but it's good to look at those to see how it all works. There's also a Khan video on it that's pretty good, so I recommend looking into pursuing that further. And here we have construct a residual plot to verify the requirements of the least squares regression model and choose the correct model below. So here what I'm going to be doing is taking the data, putting it into StatCrunch, and let me see. And then I'm going to calculate the least squares regression line. And it's simple linear. I have my X value variable, which is weight in pounds, and then miles per gallon for Y. And then I'm going to go ahead and compute this information, and I should get, let me make it a little bit bigger, this part really. Oh, there we go. So, and let's take a look at this. This is the equation. We want to make sure ours matches up with what they had. So, yeah, negative 0.007, and then they rounded to that decimal place, 73, and then 45.243 when rounding. Okay, so that looks on track. And we're looking at, here they have a fitted line for the miles per gallon and weight in pounds for X. But what we're looking to graph instead, well, that's a nice graph. We want the least squares, the residual plot, so of the least squares regression model. So what we can do is, go in here and edit, and then let's see, residuals versus X values. Okay, and then let's take a look at this. All right, so that looks, here we have the residuals on the y-axis and then the weight in pounds. And let's see if that matches up. It does. And then I noticed that this goes to 2. And okay, these go to 2, and then this one goes to 28. Our data does not look like that at all. I think that that looked more like the data from the fitted line that we saw. So that we can count out, but these all go to 2, even though they're not very, they don't go even close to 2, but let's go ahead and set our graph up similarly. So the y-axis, I'm going to put that it goes all the way to -2. So it looks closer to the ones that we're looking at, and then the max 2. Okay. And then let's go ahead and see. They start a little bit lower, but so they have 750. They're incrementing here by, it looks like 750, 250, and 500, so 750. So this at the bottom is a little bit different, but we kind of have an idea. So first thing, what can we eliminate? Well, this one for sure. And everything is not at 0, so we don't have to worry about that one at this point. And then we can look at this one. Why don't we look at this one? I think that one's pretty close. So if I see anything, and this red line is at 0. I'm not sure how to do that in StatCrunch, but we can see here, so we have 2, 4, 5, 6 numbers below that. So let's see, 2, 4, 5, 6. So that looks right. 2, 4, 5, 6. Yeah. So let's look at the other one and see if we see something a little bit different. Or so 2, 4, 5. Oh, that one's on the line. So that doesn't look right to me. But let's look at it a little bit further. It could be on the line, so hard to tell. Let's go ahead and make this one bigger too. And then, okay, so let's look at these points. So we have this labeled, so this would be -1. And so this would be -0.5, and this one looks like it's not beyond the midway between 0 and -1. So I think that this looks off to me. And also, let's see, this appears to be before this one, and this one appears after. So I'm just analyzing it and trying to look for differences, and let's take a look at this one and see if we're doing a little bit better here. Yes, that looks better to me. So I'm going to go ahead and go with that one because I think the other one is just a little bit off, but the pattern here looks very much the same. So I'm going to select C and see how that works out. All right. So interpret the coefficient of determination and comment on the adequacy of the linear model. So here we have, we calculated this earlier, 98.4%. And the variance in what am I thinking? The variance in gas mileage is explained by the linear model. The least squares regression model appears to be appropriate based on the residual plot. So here, as we talked about, the variance in gas mileage is being explained or described by the variable of x, which is the weight of the car. And this is deemed to be an appropriate model based on the residual plot. We're seeing the data really centered around 0. It's not very far off. This is just from -2 to +2, and this would happen if there were no errors at all, which wouldn't make sense. This is about the smaller the distance is between this, the smaller the residuals are, the better the standard error of the line. That the smaller the errors are, the better the fit. So this looks pretty good to me. So I'm going to go with that it is appropriate, and let's check the answer. All right, that looks good. So let me know if you have any